Introduction to Management Science. 8th edition. By Bernard W. Taylor III. Chapter 5. Forecasting. Chapter 5, Forecasting. Chapter Topics: Forecasting Components, Time Series Methods. Forecast Accuracy. Time Series Forecasting using Excel. Time Series Forecasting using QM for Windows. Regression Methods. Chapter 5, Forecasting. Forecasting Components. A variety of forecasting methods are available for use depending on the time frame of the forecast and the existence of patterns. Time frames: short range, 1 to 2 months. Medium range, 2 months to 1 or 2 years. Long range, more than 1 or 2 years. Patterns: trend, random variations, cycles, seasonal pattern. Chapter 5, Forecasting. Forecasting Components. Patterns: 1 of 2. Trend, a long-term movement of the item being forecast. Random variations, movements that are non-predictable and follow no pattern. Cycle, a movement, up or down, that repeats itself over a lengthy time span. Seasonal pattern, oscillating movement in demand that occurs periodically in the short run and is repetitive. Chapter 5, Forecasting. Forecasting Components. Patterns: 2 of 2. Trend line. Figure 5.1. Forms of forecast movement: A. Trend, B. Cycle, C. Seasonal pattern, D. Trend with seasonal pattern. Chapter 5, Forecasting. Forecasting Components. Forecasting Methods. Time series, statistical techniques that use historical data to predict future behavior. Regression methods, regression, or causal, methods that attempt to develop a mathematical relationship between the item being forecast and factors that cause it to behave the way it does. Qualitative methods, methods using judgment, expertise and opinion to make forecasts. Chapter 5, Forecasting. Forecasting Components. Qualitative methods. Qualitative methods, the jury of executive opinion, is the most common type of forecasting method for long-term strategic planning. Performed by individuals or groups within an organization, sometimes assisted by consultants and other experts, whose judgments and opinion are considered valid for the forecasting issue. Usually includes specialty functions such as marketing, engineering, purchasing, etc., in which individuals have experience and knowledge of the forecasted item. Supporting techniques included the Delphi method, market research, surveys, etc. Chapter 5, Forecasting. Time series methods overview. Statistical techniques that make use of historical data collected over a long period of time. Methods assume that what has occurred in the past will continue to occur in the future. Forecasts based on only one factor, time. Chapter 5, Forecasting. Time series method. Moving average, 1 of 5. Moving average uses values from the recent past to develop forecasts. This dampens or smooths out random increases and decreases. Useful for forecasting relatively stable items that do not display any trend or seasonal pattern. Formula for Chapter 5, Forecasting. Time series method. Moving average, 2 of 5. Example: Instant Paperclip Supply Company forecast of orders for the next month. 3-month moving average. 5-month moving average. Chapter 5, Forecasting. 3 and 5-month moving averages. Time series methods. Moving average, 3 of 5. Figure 5.2. 3 and 5-month moving averages. Chapter 5, Forecasting. 3 and 5-month moving averages. Time series methods. Moving average, 4 of 5. Figure 5.2. 3 and 5-month moving averages. Chapter 5, Forecasting. Time series method moving average, 5 of 5. Longer period moving averages react more slowly to changes in demand than do shorter period moving averages. The appropriate number of periods to use often requires trial and error experimentation. Moving average does not react well to changes, trends, seasonal effects, etc., but is easy to use and inexpensive. Good for short-term forecasting. Chapter 5, Forecasting. Weighted moving average, 1 of 2. Time series method. Weighted moving average, 1 of 2. In a weighted moving average, weights are assigned to the most recent data. Formula. Chapter 5, Forecasting. Weighted moving average, 2 of 2. Time series method. Weighted moving average, 2 of 2. Determining precise weights and number of periods requires trial and error experimentation. Chapter 5, Forecasting. Exponential smoothing, 1 of 11. Time series method. Exponential smoothing, 1 of 11. Exponential smoothing weights recent past data more strongly than more distant data. Two forms, simple exponential smoothing and adjusted exponential smoothing. Simple exponential smoothing. Ft plus 1 equals dt plus 1, Ft. Where Ft plus 1 equals the forecast for the next period. Dt equals actual demand in the present period. Ft equals the previously determined forecast for the present period. Equals a weighting factor, smoothing constant. Use F1 equals D1. Chapter 5, Forecasting. Exponential smoothing, 2 of 11. Time series method. Exponential smoothing, 2 of 11. The most commonly used values of are between 0.10 and 0.50. Determination of is usually judgmental and subjective and often based on trial and error experimentation. Chapter 5, Forecasting. Exponential smoothing, 3 of 11. Time series method. Exponential smoothing, 3 of 11. Example, Prime Minister Computer Services, see Table 5.4. Exponential smoothing forecast using smoothing constant of 0.30. Forecast for period 2, February. F2 equals D1 plus, 1 F1 equals, 0.3037, plus, 0.7037, equals 37 units. Forecast for period 3, March. F3 equals D2 plus, 1 F2 equals, 0.3040, plus, 0.7037, equals 37.9 units. Chapter 5, Forecasting. Exponential smoothing forecasts, equals 0.30 and equals 0.50. Time series method. Exponential smoothing, 4 of 11. Using F1 equals D1. Table 5.4. Exponential smoothing forecasts, equals 0.30 and equals 0.50. Chapter 5, Forecasting. Exponential smoothing, 5 of 11. Time series method. Exponential smoothing, 5 of 11. The forecast that uses a higher smoothing constant, 0.50, reacts more strongly to changes in demand than does the forecast with a lower constant, 0.30. Both forecasts lag behind actual demand. Both forecasts tend to be consistently lower than actual demand. Low smoothing constants are appropriate for stable data without trend, higher constants appropriate for data with trends. Chapter 5, Forecasting. Exponential smoothing forecasts. Time series method. Exponential smoothing, 6 of 11. Figure 5.3. Exponential smoothing forecasts. Chapter 5, Forecasting. Exponential smoothing, 7 of 11. Time series method. Exponential smoothing, 7 of 11. Adjusted exponential smoothing with a trend adjustment factor added. Formula: aft plus 1 equals ft plus 1 plus tt plus 1, where tt equals an exponentially smooth trend factor. Tt plus 1 equals ft plus 1, ft, plus 1, tt. Tt equals the last, previous, period trend factor. Equals smoothing constant for trend, valued between 0 and 1. Reflects the weight given to the most recent trend data. Determined subjectively. Chapter 5, Forecasting. Exponential smoothing, 8 of 11. Time series methods. Exponential smoothing, 8 of 11. Example: Prime Minister Computer Services and exponential smooth. Forecasts with equals 0.50 and equals 0.30, see table 5.5. Start with T2 equals 0.00. Adjusted forecast for period 3. T3 equals F3, F2, plus 1, T2. Equals 0.30 38.5 to 37.0, plus 0.700, equals 0.45. AF3 equals F3 plus T3 equals 38.5 plus 0.45 equals 38.95. Chapter 5, Forecasting. Exponential smoothing, 9 of 11. Time series methods. Exponential smoothing, 9 of 11. Tt plus 1 equals Ft plus 1, Ft, plus 1, Tt. Table 5.5. Adjusted exponentially smooth forecast values. Chapter 5, Forecasting. Exponential smoothing, 10 of 11. Time series methods. Exponential smoothing, 10 of 11. Adjusted forecast is consistently higher than the simple exponentially smooth forecast. It is more reflective of the generally increasing trend of the data. Chapter 5, Forecasting. Adjusted exponentially smooth forecast. Time series methods. Exponential smoothing, 11 of 11. Figure 5.4. Adjusted exponentially smooth forecast. Chapter 5, Forecasting. Time series methods. Linear trend line, 1 of 5. When demand displays an obvious trend over time, a least squares regression line, or linear trend line, can be used to forecast. Formula. Chapter 5, Forecasting. Time series methods. Linear trend line, 2 of 5. Example: Prime Minister Computer Services, see table 5.6. Chapter 5, Forecasting. Time series methods. Linear trend line, 3 of 5, table 5.6. Least squares calculations. Chapter 5, Forecasting. Time series methods. Linear trend line, 4 of 5. A trend line does not adjust to a change in the trend as does the exponential smoothing method. This limits its use to shorter time frames in which trend will not change. Chapter 5, Forecasting. Time series methods. Linear trend line, 5 of 5, figure 5.5. Chapter 5, Forecasting. Seasonal adjustments, 1 of 4. Time series methods. Seasonal adjustments, 1 of 4. A seasonal pattern is a repetitive up and down movement in demand. Seasonal patterns can occur on a monthly, weekly, or a daily basis. A seasonally adjusted forecast can be developed by multiplying the normal forecast by a seasonal factor. A seasonal factor can be determined by dividing the actual demand for each seasonal period by total annual demand. C equals D/D. Chapter 5, Forecasting. Seasonal adjustments, 2 of 4. Time series methods. Seasonal adjustments, 2 of 4. Seasonal factors lie between 0 and 1 and represent the portion of total annual demand assigned to each season. Seasonal factors are multiplied by annual demand to provide adjusted forecasts for each period. Chapter 5, Forecasting. Demand for turkeys at Wishbone Farms. Time series methods. Seasonal adjustments, 3 of 4. Example, Wishbone Farms. Table 5.7. Demand for turkeys at Wishbone Farms. S1 equals D1 slash D equals 42.0 148.7 equals 0.28. S2 equals D2 slash D equals 29.5 148.7 equals 0.20. S3 equals D3 slash D equals 21.9 148.7 equals 0.15. S4 equals D4 slash D equals 55.3 148.7 equals 0.37. Chapter 5, Forecasting, Seasonal Adjustments, 4 of 4. Time series methods. Seasonal adjustments, 4 of 4. Multiply forecasted demand for entire year by seasonal factors to determine quarterly demand. Forecast for entire year, trendline for data in table 5.7. Y equals 40.97 plus 4.30 x equals 40.97 plus 4.304 equals 58.17. Seasonally adjusted forecasts. SF1 equals, S1F5, equals, 0.2858.17, equals 16.28. SF2 equals, S2F5, equals, 0.2058.17, equals 11.63. SF3 equals, S3F5, equals, 0.1558.17, equals 8.73. SF4 equals, S4F5, equals, 0.3758.17, equals 21.53. Note the potential for confusion, the CR seasonal factors, fractions. Whereas the SPR seasonally adjusted forecasts, commodity values. Chapter 5, Forecasting. Forecast Accuracy Overview. Forecasts will always deviate from actual values. Difference between forecasts and actual values referred to as forecast error. Would like forecast error to be as small as possible. If error is large, either technique being used is the wrong one, or parameters need adjusting. Measures of forecast errors. Mean absolute deviation, MAD. Mean absolute percentage deviation, MAPD. Cumulative error, E-bar. Average error, or bias, E. Chapter 5, Forecasting. Mean absolute deviation, 1 of 7. Forecast accuracy. Mean absolute deviation, 1 of 7. MAD is the average absolute difference between the forecast and actual demand. Most popular and simplest to use measures of forecast error. Formula. Chapter 5, Forecasting. Mean absolute deviation, 2 of 7. Forecast accuracy. Mean absolute deviation, 2 of 7. Example, Prime Minister Computer Services, see Table 5.8. Compare accuracies of different forecasts using MAD. Chapter 5, Forecasting. Computational values for MAD. Forecast accuracy. Mean absolute deviation, 3 of 7. Table 5.8. Computational values for MAD. Chapter 5, Forecasting. Mean absolute deviation, 4 of 7. Forecast accuracy. Mean absolute deviation, 4 of 7. The lower the value of MAD relative to the magnitude of the data, the more accurate the forecast. When viewed alone, MAD is difficult to assess. Must be considered in light of magnitude of the data. Chapter 5, Forecasting. Mean absolute deviation, 5 of 7. Forecast accuracy. Mean absolute deviation, 5 of 7. Can be used to compare accuracy of different forecasting techniques working on the same set of demand data, Prime Minister Computer Services. Exponential smoothing, equals 0.50, MAD equals 4.04. Adjusted exponential smoothing, equals 0.50, equals 0.30, MAD equals 3.81. Linear trend line, MAD equals 2.29. Linear trend line has lowest MAD, increasing from 0.30 to 0.50 improves smooth forecast. Chapter 5, Forecasting. Mean absolute deviation, 6 of 7. Forecast accuracy. Mean absolute deviation, 6 of 7. A variation on MAD is the mean absolute percent deviation, MAPD. Measures absolute error as a percentage of demand rather than per period. Eliminates problem of interpreting the measure of accuracy relative to the magnitude of the demand and forecast values. Formula. Chapter 5, Forecasting. Mean absolute deviation, 7 of 7. Forecast accuracy. Mean absolute deviation, 7 of 7. Mapped for other 3 forecasts. Exponential smoothing, equals 0.50, mapped equals 8.5%. Adjusted exponential smoothing, equals 0.50, equals 0.30. Mapped equals 8.1%. Linear trend, mapped equals 4.9%. Chapter 5, Forecasting. Forecast accuracy cumulative error, 1 of 2. Cumulative error is the sum of the forecast errors, E equals A. A relatively large positive value indicates forecast is biased low, a large negative value indicates forecast is biased high. If preponderance of errors are positive, forecast is consistently low, and vice versa. Cumulative error for trend line is always almost zero, and is therefore not a good measure for this method. Cumulative error for Prime Minister Computer Services can be read directly from Table 5.8. E equals at equals 49.31 indicating forecasts are frequently below actual demand. Chapter 5, Forecasting. Forecast accuracy cumulative error, 2 of 2. Cumulative error for other forecasts. Exponential smoothing, equals 0.50, E equals 33.21. Adjusted exponential smoothing, equals 0.50, equals .30. E equals 21.14. Average error, bias, is the per period average of cumulative error. Average error for exponential smoothing forecast. A large positive value of average error indicates a forecast is biased low, a large negative error indicates it is biased high. Chapter 5, Forecasting. Comparison of forecasts for Prime Minister Computer Services. Forecast accuracy. Example forecasts by different measures. Table 5.9. Comparison of forecasts for Prime Minister Computer Services. Results consistent for all forecasts. Larger value of alpha is preferable. Adjusted forecast is more accurate than exponential smoothing forecasts. Linear trend is more accurate than all the others. Chapter 5, Forecasting. Time series forecasting using Excel, 1 of 4. Exhibit 5.1. Chapter 5, Forecasting. Time series forecasting using Excel, 2 of 4. Exhibit 5.2. Chapter 5, Forecasting. Time series forecasting using Excel, 3 of 4. Exhibit 5.3. Chapter 5, Forecasting. Time series forecasting using Excel, 4 of 4. Exhibit 5.4. Chapter 5, Forecasting. Exponential smoothing forecast with Excel QM. Exhibit 5.5. Chapter 5, Forecasting. Time series forecasting solution with QM for Windows, 1 of 2. Exhibit 5.6. Chapter 5, Forecasting. Time series forecasting solution with QM for Windows, 2 of 2. Exhibit 5.7. Chapter 5, Forecasting. Regression methods overview. Time series techniques relate a single variable being forecast to time. Regression is a forecasting technique that measures the relationship of one variable to one or more other variables. Simplest form of regression is linear regression. Chapter 5, Forecasting. Regression methods. Linear regression. Linear regression relates dependent variable, to an independent variable. Linear function. Chapter 5, Forecasting. Linear regression. Example, 1 of 3. Regression methods. Linear regression. Example, 1 of 3. State University Athletic Department. Chapter 5, Forecasting. Linear regression. Example, 2 of 3. Regression methods. Linear regression. Example, 2 of 3. Chapter 5, Forecasting. Linear regression. Example, 3 of 3. Regression methods. Linear regression. Example, 3 of 3. Figure 5.6. Linear regression line. Chapter 5, Forecasting. Regression methods. Correlation, 1 of 2. Correlation is a measure of the strength of the relationship between independent and dependent variables. Formula. Value lies between +1 and -1. Value of 0 indicates little or no relationship between variables. Values near 1.00 and -1.00 indicate strong linear relationship, correlation and anti-correlation. Chapter 5, Forecasting. Regression methods. Correlation, 2 of 2. Value for State University. Example. Chapter 5, Forecasting. Coefficient of determination. Regression methods. Coefficient of determination. The coefficient of determination is the percentage of the variation in the dependent variable that results from the independent variable. Computed by squaring the correlation coefficient, R. For State University. Example. R equals 0.948, R2 equals 0.899. This value indicates that 89.9% of the amount of variation in attendance can be attributed to the number of wins by the team, with the remaining 10.1% due to other, unexplained, factors. Chapter 5, Forecasting. Regression analysis with Excel, 1 of 7. Exhibit 5.8. Chapter 5, Forecasting. Regression analysis with Excel, 2 of 7. Exhibit 5.9. Chapter 5, Forecasting. Regression analysis with Excel, 3 of 7. Exhibit 5.10. Chapter 5, Forecasting. Regression analysis with Excel, 4 of 7. Exhibit 5.11. Chapter 5, Forecasting. Regression analysis with Excel, 5 of 7. Exhibit 5.12. Chapter 5, Forecasting. Regression analysis with Excel, 6 of 7. Exhibit 5.13. Chapter 5, Forecasting. Regression analysis with Excel, 7 of 7. Exhibit 5.14. Chapter 5, Forecasting. Regression analysis with QM for Windows. Exhibit 5.15. Chapter 5, Forecasting. Multiple regression with Excel, 1 of 4. Multiple regression relates demand to 2 or more independent variables. General form. Y equals 0 plus 1 by 1 plus 2 by 2 plus kxk, where 0 equals the intercept. 1. K equals parameters representing contributions of the independent variables. x1, xk equals independent variables. Chapter 5, Forecasting. Multiple regression with Excel, 2 of 4. State University. Example. Chapter 5, Forecasting. Multiple regression with Excel, 3 of 4. Exhibit 5.16. Chapter 5, Forecasting. Multiple regression with Excel, floor of 4. Exhibit 5.17. Chapter 5, Forecasting. Example problem solution computer software firm, 1 of 4. Problem statement. For data below, develop an exponential smoothing forecast using equals 0.40, and an adjusted exponential smoothing forecast using equals 0.40 and equals 0.20. Compare the accuracy of the forecasts using MAD and cumulative error. Chapter 5, Forecasting. Example problem solution computer software firm, 2 of 4. Step 1. Compute the exponential smoothing forecast. Ft plus 1 equals dt plus 1, Ft. Step 2. Compute the adjusted exponential smoothing forecast. Ft plus 1 equals Ft plus 1 plus Tt plus 1. Tt plus 1 equals Ft plus 1, Ft, plus 1, Tt. Chapter 5, Forecasting. Example problem solution computer software firm, 3 of 4. Chapter 5, Forecasting. Example problem solution computer software firm, 4 of 4. Step 3. Compute the MAD values. Step 4. Compute the cumulative error. EFT equals 35.97. EAFT equals 30.60. Chapter 5, Forecasting. Example problem solution building products store, 1 of 5. Problem statement. For the following data, develop a linear regression model. Determine the strength of the linear relationship using correlation. Determine a forecast for lumber given 10 building permits in the next quarter. Chapter 5, Forecasting. Example problem solution building products store, 2 of 5. Chapter 5, Forecasting. Example problem solution building products store, 3 of 5. Step 1. Compute the components of the linear regression equation. Chapter 5, Forecasting. Example problem solution building products store, 4 of 5. Step 2. Develop the linear regression equation. Y equals a plus bx, y equals 1.36 plus 1.25x. Step 3. Compute the correlation coefficient. Chapter 5, Forecasting. Y equals a plus bx equals 1.36 plus 1.25 10 equals 13.86 or 1386 board foot. Example problem solution. Building products store, 5 of 5. Step 4. Calculate the forecast for x equals 10 permits. Y equals a plus bx equals 1.36 plus 1.25 10 equals 13.86 or 1386 board foot. Chapter 5, Forecasting.